Okay, so this is pretty wild, right? We've got this language model. It can basically fit on your phone, you know,
Yeah, only 3.8 billion parameters. It's called Phi-4-Mini.
tiny. And it's not just compact, it can actually go head to head with these much larger open source models.
It's beating them, actually, in some cases.
And get this, it can even hold its own on these crazy complex reasoning tasks in math and coding.
Stuff you'd think would need a model twice its size.
Exactly. It really makes you rethink what's possible with these smaller AI models.
It's really exciting, academically speaking, because it kind of throws a wrench in that whole bigger is always better idea.
Right?
It really highlights the importance of clever design and using top-notch data, maybe even more so than just adding more parameters.
It's all about efficiency, squeezing the most out of every bit of information.
And you actually sent over the technical report about this whole Phi-4 family of models, right?
Yes, for Microsoft.
It's a pretty fascinating deep dive into how they achieve this.
And that's precisely what we're here to do today. We're going to unpack all the really cool, academically juicy myths of Phi-4, specifically Phi-4-Mini and its even more impressive sibling, Phi-4 Multimodal.
Multimodal, oh boy.
So for our listeners who are always hungry for a deeper dive into these advancements, but maybe don't have time to wade through dense technical papers, fear not. We're going to make it crystal clear, breaking it down in a way that's insightful and engaging.
Yeah, our goal is to extract those core innovative principles behind these models. How do they perform so well given their compact size?
Yeah, and how do they even manage to work with not just text, but also images and sounds all the same time? That's the multimodal part.
Right, a unified approach is pretty groundbreaking.
So let's get right into it, starting with Phi-4-Mini and the innovations they made in terms of pure language processing.
Okay, sounds good.
The first thing that jumped out at me was how much emphasis they put on the quality of the data. They specifically call out high-quality web and synthetic data, particularly data sets focused on math and coding.
Yeah, that's a key innovation right there. They've got a specific recipe for creating this synthetic data.
A recipe, like baking a cake.
Sort of. It's about carefully selecting and even generating data that's designed to boost the model's reasoning and problem-solving skills.
So it's not just about feeding it tons of data, it's about being super picky and even creating custom-made data.
Exactly. And that shift in thinking from quantity to quality is becoming increasingly important in AI, especially when you're working with smaller models.
And it's not just what's in the data. They also decided to significantly increase the vocabulary size to 200,000 tokens. What's the big deal about that from an academic perspective?
So tokens are like the building blocks of language for these models. Think of them as the individual units the AI works with.
Okay, got it.
A larger vocabulary means the model can represent a much wider range of words and ideas directly, without having to break them down into smaller pieces.
I see. So it's like having a richer set of tools to work with.
Exactly. And this is especially important for languages other than English and for handling really specialized vocabulary, like in coding or math.
So it makes it more multilingual and better at understanding technical language.
Precisely.
Cool. Now, moving on to the architecture of Phi-4-Mini, they've introduced some pretty interesting elements, specifically group query attention, or GQA, and a fractional rape dimension. Could you break those down for us? They sound a bit intimidating.
Sure, let's start with GQA. So, you know how a lot of modern language models are based on this thing called a transformer architecture?
Yeah, I've heard the term thrown around.
Okay, good. Now, transformers use this attention mechanism, which basically helps the model focus on the most important parts of a text as it's reading it. To do this, they have to keep track of everything they've processed so far, sort of like a short-term memory.
A mental notepad, if you will.
Exactly. But when you're dealing with super long chunks of text, keeping track of everything can become a real resource hog. That's where GQA comes in. It allows multiple parts of the attention mechanism to share a smaller pool of memory resources.
So it's like a group project where everyone shares the same whiteboard instead of each person having their own.
Yes, a perfect analogy. And this makes it way more efficient for the model to process and even generate really long sequences of text, which is why they can handle up to 128,000 tokens at a time.
That's pretty impressive. And what about this fractional rope dimension?
Right, so rope, or rotary position and bearing, is all about understanding the order of words in a sentence. It encodes information about where each word sits in the sequence.
Because word order matters a lot for meaning, right?
Absolutely. Now, the fractional part means they're not using the full capacity of the attention mechanism to encode this positional information. They keep about a quarter of it free, which actually helps the model handle these super long contexts even better.
So it's about finding the right balance between knowing word order and having the flexibility to deal with long-range dependencies in the text.
Exactly. It's a subtle but really important innovation.
That's fascinating. Now, let's talk about the experimental version of Phi-4-Mini, the one they specifically designed for reasoning. The training process for this model sounds particularly interesting.
Yeah, they took a really multi-pronged approach to this one. First, they pre-trained it on a massive data set of something like 60 billion reasoning code T tokens.
Code T tokens, what are those?
Code T stands for chain of thought. It's a way of making the model explicitly spell out the steps it takes to reach a conclusion, like a little detective laying out the clues.
So it's not just about getting the right answer, it's about showing its work.
Exactly. This pre-training stage basically teaches the model how to think a step by step. Then they fine-tuned it on a smaller but super high-quality set of human annotated examples, making sure it was learning to reason correctly.
So they started broad and then got really specific and focused.
Right. And then they use this technique called rollout DPO, which essentially uses human feedback to tell the model which reasoning paths are better than others.
So it's like a teacher giving feedback on a student's thought process, helping them refine their logic.
Precisely. And the results they got from this model are pretty remarkable, especially considering its size.
Yeah, it seems to be on par with or even outperforming much larger models like DeepSeek.
Which really highlights the effectiveness of this training strategy, right? Combining synthetic data for pre-training, carefully selected human examples for fine-tuning, and then this preference-based learning for the final polish.
It suggests that maybe size isn't everything. You can achieve some seriously impressive cognitive abilities with a smaller model if you train it the right way.
Exactly.
So to sum up Phi-4-Mini's language innovations, what would you say are the most academically significant contributions?
Well, for a model of its size, it's achieving state-of-the-art performance on a whole range of natural language tasks, including understanding, generating text, and even reasoning. It's also really good at math and code, all within a relatively small 3.8 billion parameter footprint.
Right, that's pretty impressive considering some models out there are tens or even hundreds of billions of parameters.
And it's all thanks to that focus on high-quality, carefully crafted data, those architectural efficiencies from GQA and fractional rope, and that multi-stage reasoning training process.
All right, so let's shift gears and dive into the really cool stuff, the multimodal aspect of Phi-4.
Phi-4 multimodal. This is where things get really interesting.
Yeah, it's arguably the most innovative part of the whole Phi-4 family. So what sets Phi-4 multimodal apart is its ability to handle not just text, but also images and audio, all within a single model.
That's the key, a unified approach.
Right, it can basically see, hear, and read all at the same time. Why is that such a big deal compared to how things were done before?
Well, in the past, if you wanted an AI that could deal with multiple modalities, you basically had to create separate models for each one. You'd have a model for vision, a model for language, a model for audio.
And then try to stitch them together somehow?
Exactly. And that was a real challenge. It could lead to all sorts of problems with performance and efficiency. Phi-4 Multimodal takes a completely different approach. It processes all these different types of information within a single integrated system.
So it's like a single brain that can handle all these senses at once instead of having separate, specialized modules.
Yeah, it's a much more elegant and potentially powerful approach.
And the secret sauce behind this unified approach seems to be this thing called the Mixture-of-LoRAs technique. Could you break that down for us?
So LoRa stands for low-rank adaptation. It's a clever way of adapting large language models to new tasks without having to retrain the entire model.
So it's like giving the model a specialized upgrade without having to rebuild the whole thing from scratch.
Exactly. Now, the Mixture-of-LoRAs takes this concept and applies it to different modalities. They basically create these specialized LoRa adapters, one for vision, one for speech audio, and potentially more for other modalities in the future.
So each adapter is like a specialist that can handle a specific type of input.
Precisely. And they also have these routers that direct the incoming data to the right adapter. So if you give the model an image, the router sends it to the vision adapter. If you give it audio, it goes to the audio adapter.
And the cool part is that the core language model itself remains untouched. It's like adding new skills to a person without changing their fundamental personality.
Yeah, that's one of the big advantages of this design. It allows you to add multimodal capabilities without messing up the model's original ability to understand and generate language.
Right, because sometimes when you fine-tune a model too much on new tasks, it can forget what it learned before.
Exactly. But with this modular approach, you get the best of both worlds. You have a strong language model at the core, and then you can add on these specialized modules as needed.
And it's also super extensible, right? If you wanted to add support for a new modality, like say touch or smell, you could theoretically just train a new LoRa adapter and update the router.
Exactly. It's a very flexible system, which makes it super exciting for future research.
That modularity is really powerful. Okay, let's get into the specifics of how Phi-4 multimodal handles vision. What are the key components of the visual pathway?
So for vision, they use a model called Siglet 400M as the visual encoder. This model is responsible for extracting meaningful visual features from images.
So it's like the eyes of the model, so to speak.
Yeah, you could say that. And they've fine-tuned this encoder using a technique called LLM2 CLMLP, which basically makes it better at aligning visual information with language.
So it's learning to see the world in a way that makes sense to the language model.
Right, and then those visual features are converted into a format that the language model can understand using a two-layer MLP, which stands for multi-layer perceptron. Think of it as a translator between vision and language.
And then finally, there's a vision-specific LoRa adapter called LoRath.
Exactly. This adapter is specifically trained to help the language model incorporate visual information into its understanding and generation processes.
So it's like teaching the language model how to think about what it sees.
Right. And another cool detail here is their dynamic multi-crop strategy. It basically allows the model to efficiently process images of different sizes and shapes by intelligently selecting multiple crops from each image.
So instead of resizing every image to a fixed size, which could lead to information loss, it dynamically focuses on the most important parts of the image.
Exactly. It's a clever way of making the model more robust and efficient, especially when dealing with real-world images that come in all sorts of shapes and sizes.
So it's like having a photographer who knows how to frame a shot perfectly, regardless of the scene.
A great analogy.
Okay, let's move on to the speech and audio side of things. What are the key components of the audio pathway?
For audio, they use a different type of encoder, one based on conformer blocks. These are really good at capturing the temporal dependencies in audio signals, meaning they can understand how sounds change over time.
So they're like the ears of the model tuned to the nuances of sound.
Exactly, and they use a standard 80-dimensional representation of the audio features.
80 dimensions, that's a lot.
Well, sound is complex. And just like with vision, they use a two-layer MLP to project the audio features into the language embedding space.
So it's that same translation process, but this time from sound to language.
Right, and then there's an audio-specific LoRa adapter called LoRa-A, which helps the language model make sense of the sounds it's hearing.
It's amazing how they've managed to create this parallel architecture for both vision and audio, using the same basic principles but with specialized components for each modality.
Yeah, it's a very elegant design, and it's not just the architecture that's interesting. The training process for Phi-4 multimodal is also pretty sophisticated. Tell me more about that. So they have separate training stages for vision and speech audio.
Okay, why is that?
Well, vision and audio are pretty different beasts, so it makes sense to train them separately to start with. For vision, they have a four-stage process.
4 stages.
Yeah, it's pretty involved. First, they align the vision projector with the language model's understanding of text. Then they train the vision encoder and projector together on a massive data set of images.
So it's like teaching the model to see and understand images in a way that aligns with its existing knowledge of language.
Exactly. Then in the third stage, they train the LoRav adapter along with the vision encoder and projector, using pairs of images and text.
So it's learning to generate descriptions of images and understand the relationship between what it sees and what it can say about it.
Right. And finally, they train the model on sequences of images, which helps it understand the temporal flow of visual information.
Like a video, basically.
Yes, exactly.
Wow, that's a lot of training. And what about the speech and audio training?
For speech and audio, they have a two-stage process. The first stage is all about aligning the audio encoder with the language model, using a huge amount of automatic speech recognition data, which is basically transcripts of spoken audio.
So it's learning to convert speech into text.
Exactly. And then in the second stage, they fine-tune the audio projector and LoRa-A adapter using a curated data set of speech and audio instruction following examples.
So it's learning to understand and respond to spoken commands and instructions.
Precisely. And it's worth noting that they specifically trained it on audio up to 30 minutes long for speech summarization.
Speech summarization, that sounds incredibly useful.
It is. It means the model can listen to a long audio recording and then generate a concise summary of the key points.
Wow, that's pretty amazing. And after all this modality-specific training, they also do a joint training phase involving both vision and speech.
Yeah, that's the final step. The idea is to teach the model to understand the interplay between what it sees and what it hears.
So it's learning to integrate information from both modalities.
Exactly.
So after all this comprehensive training, how does Phi-4 multimodal actually perform?
It performs incredibly well. On standard vision language benchmarks, it beats their previous work by a significant margin and outperforms other open source models of similar size.
So it's pushing the boundaries of what's possible, smaller models.
Yeah, and what's really impressive is that it even achieves competitive results with some much larger closed-source models on tasks that require a deep understanding of both images and language.
Like understanding charts or scientific diagrams.
Exactly. And in vision speech tasks, it also shows significant improvements over other models.
And perhaps most notably, it achieves state-of-the-art performance on multilingual speech recognition and translation.
It even ranked at the top of the OpenISR leaderboard.
Wow, top of the leaderboard. That's a huge accomplishment, especially for a model of its size.
It is, and it's also the first open source model with really good speech summarization capabilities.
Which is a major step forward.
It is, and all of this really highlights the effectiveness of their Mixture-of-LoRAs framework.
It's a really innovative way to build multimodal AI systems.
Yeah, it allows you to get strong performance on multimodal tasks without sacrificing the core language capabilities of the model.
It's the best of both worlds.
Exactly.
So, zooming out a bit, what are the biggest academic takeaways from the Phi-4 family, especially from a research perspective?
I think the main takeaway is that we can achieve some really impressive performance and even novel capabilities like unified multimodality by focusing on clever architectural designs and carefully curating the data we use to train these models.
It's not just about brute force, throwing more parameters at the problem.
Exactly. And the Mixture-of-LoRAs technique in particular is a really promising approach for building multimodal AI systems that are both powerful and efficient.
And the fact that they've made all of this open source is a huge contribution to the research community.
Absolutely. It allows researchers to build on their work and explore new possibilities.
So, to wrap up, what are the most important innovations from Phi-4 that our listeners should remember?
First, the power of carefully curated and even synthetic data for training smaller language models. Second, the efficiency gains they achieved through innovations like group query attention and the fractional rope dimension. Third, the Mixture-of-LoRAs technique as a groundbreaking way to build multimodal AI systems. And finally, the multi-stage reasoning training methodology that shows how we can enhance the cognitive abilities of smaller models.
So, it's all about working smarter, not harder.
Exactly.
And for our listeners, we hope this deep dive has given you a clear understanding of these cutting-edge advancements and maybe even sparked some new ideas about the future of AI research.
It makes you wonder, given these advances in efficiency and multimodality, what new applications for AI might become possible, especially in areas that require a holistic understanding of different types of data.
That's a great question to ponder, and if you're interested in learning more, we highly recommend checking out the technical report. Thanks for joining us on this exciting journey.
Thanks for having me.
It's been a pleasure.